Hello and welcome to ICMR NIE's online course on causal inference from observational studies, NISA 201. Welcome to the topic Measures of Causal Effect in Cohort Studies. Measures of effect and measures of association are different terms. A measure of effect compares what would happen to one population under two possible but distinct conditions. It is a theoretical or a metaphysical concept. It is logically impossible to observe one population under both the conditions at the same time. Hence, it is logically impossible to see directly the size of the effect. Whereas measure of association compares what happens in two distinct populations. In this case, we can observe both populations and directly observe an association. For example, we could calculate the ratio of lung cancer incidence rates for males and females. The rate ratio for lung cancer comparing the male and female subpopulation is not an effect measure because its two component rates refer to different groups of people. In this example, the rate ratio is a measure of association. We could present the data of an analytical cohort study in a 2 by 2 table. L1 is the total number of persons exposed. Among the exposed, A is the number of persons who are found to be ill. Similarly, L0 is the total number of persons unexposed. Among the unexposed, C is the number of persons who are found to be ill. In a cohort study, we can measure the frequency with which the outcome occurs. This could be either a risk or a rate. The risk of developing illness among the exposed individuals, R1, is number of exposed individuals who became ill, that is A, divided by L1. The risk of developing illness among the unexposed individual, R0, is the number of exposed individuals who became ill, that is C divided by L0. There are different approaches to compare risk in a cohort study. First, additive approach, that is called risk difference, is also referred as absolute measures. The second is multiplicative approach, that is risk ratio, rate ratio, or an exposure odds ratio. They are also referred as relative measures. Risk difference is the difference in risk between exposed and unexposed groups in a population. We may also refer to this as excess risk. Whereas rate difference is if we use the measure of occurrence in person time. We express these difference measures in units, that is cases per unit person time for the rate difference, cases per person for the risk difference. Now let us go through an example. In 2004, a cluster of Kala-Azar cases was reported in Chhatrakali, West Bengal, India. A retrospective cohort study was conducted to estimate the incidence of infection and identify the risk factors for infection. The study investigated the presence or absence of water bodies within 25 meters of the house as one of the exposure. The risk of having leishmaniasis among those living in a house having a water body within 25 meters is 22%. The risk of having leishmaniasis among those living in a house that doesn't have a water body within 25 meters is 9%. In this example, the risk difference is 22% minus 9%, that is 13%. The risk ratio is calculated by dividing the risk in the exposed group, that is A divided by L1, by the risk in the unexposed group, that is C divided by L0. Compared to difference measures, ratio measures are dimensionless because the units cancel upon division. The risk ratio is a better indicator of strength of association compared to the risk difference. It's because it is presented in relation to a baseline occurrence level. Unlike the risk difference, the risk ratio is influenced by the baseline incidence rate. Populations sharing similar risk differences may have significantly different risk ratios depending on the magnitude of the baseline rates. How do we interpret a risk ratio? If RR is equal to 1, incidence in exposed and unexposed is same. Here exposure is not associated with disease. If risk ratio is more than 1, incidence in exposed is higher than unexposed. Here exposure is positively associated with disease. If RR is less than 1, incidence in exposed is lower than unexposed. Exposure is negatively associated with disease. Coming back to the example, the cohort study investigated the presence or absence of water bodies within 25 meters of the house as one of the exposure for leishmaniasis. The risk of having leishmaniasis among those living in a house having a water body within 25 meters is 22%. The risk of having leishmaniasis among those living in a house that doesn't have a water body within 25 meters is 9%. The risk ratio is 22% divided by 9% is 2.5. In a cohort study, we could also measure rate ratio. Person time is calculated by the sum of total time all individuals remain in the study without developing the outcome of interest. A rate is the number of new cases of a health outcome divided by total person time at risk for the population. Here the rate ratio is can be calculated by dividing rate 1 among the exposed persons by rate 0 among non-exposed persons. Odds is the ratio of probability of the event occurring or the probability of the event not occurring. We can also calculate the disease odds ratio in a cohort study. First, we calculate the odds of disease among those exposed. Here, the numerator will be the probability that the disease will develop in exposed person, that is A divided by L1, and the denominator will be the probability that they will not develop the disease among exposed persons, that is B divided by L1. Simply, the odds of disease among those exposed is A by B. Similarly, we can calculate the odds of disease among those unexposed, C by D. Dividing the odds of disease among those exposed by the odds of disease among those unexposed gives us disease odds ratio, that is AD by BC, or simply cross products ratio. There are three reasons why we prefer using risk ratios over disease odds ratios in a cohort study. First, the risk ratio corresponds to an intuitive notion. Second, the OR is less meaningful to most readers. And third, OR is larger than the risk ratio. We can calculate exposure odds ratio in a cohort study. First, we calculate the odds of exposure among those who are ill. Here, the numerator will be the probability that the person is likely to be exposed among those who are ill, that is A by A plus C. And the denominator will be the probability of being unexposed among those who are ill, that is C divided by A plus C. Simply, the odds of exposure among those who are ill is A by C. Similarly, we can calculate the odds of exposure among those not having illness, that is B divided by D. Dividing the odds of exposure among those who are ill by the odds of exposure among those who are not ill gives us exposure odds ratio, that is AD by BC, or simply the cross products ratio. In a cohort study, the ratio of the odds of disease among exposed and unexposed is equal to the ratio of the odds of exposure among ill and not ill. If the disease being studied doesn't occur frequently, B will be almost equal to A plus B and D will be almost equal to C plus D. Here the risk ratio for rare diseases will be AD by BC. In a cohort study, when the disease is rare, the ratio of the odds of disease is almost equal to the risk ratio. In ideal randomized experiments, association is causation. Association measures can be interpreted as effect measures because randomization ensures that the exposed and unexposed are exchangeable. On the other hand, in observational studies, association is not generally causation. Association measures cannot be interpreted as effect measures because the exposed and the unexposed are not generally exchangeable. Conditional exchangeability is a key condition for causal inference, irrespective of the analytical approach used to compute the causal effect. The causal effect can only be identified by using the observational data plus an assumption regarding the unmeasured risk factors. This identifying assumption is external to the data. Investigators make the assumption based on their causal theories. This identifying assumption is also known as the assumption of no unmeasured confounding given the measured variables. Additional conditions that are required for causal inference include accurate data measurement, data missing at random, and no interaction between subjects. Thank you.